All right, thank you very much. You're all very welcome to this evening's lecture, which is a joint session between Engineers Ireland Civil Division, that's ourselves, SIWEM, and the Water and Environment Society in Engineers Ireland. So you're all very welcome. Now, tonight's lecture is very topical. It's about integrated catchment management, benefits and opportunities for modelling in Ireland and abroad. The lecture this evening is given by Marie Conlon from Jacobs, Peter Smith and Colin Horn, both from Jacobs as well, and you're all very welcome. So just very quickly, Marie is a chartered engineer with over 9 years experience postgraduate, and over the past 6 years she's been developed her hydraulic modelling skills to do, and currently manages a number of projects within Jacobs. Colin is a chartered engineer with over 40 years experience in local authorities and consultants, and has been involved in hydraulic modelling and drainage area studies from the late 1980s. So, and currently manages the waste and water modelling team for the UK board in Manchester. Peter's chartered engineer, 20 years experience with river and drainage flood risk management, currently divisional director at Jacobs. In the water team, he has been responsible for overseeing the Jacobs modelling project and teams within Ireland. So you're all very welcome. We will have a lecture for about an hour. After that, we'll have a good Q&A session, and we'll wrap up at that stage. Okay, over to yourselves, and thank you very much.
Good evening. Thanks very much for everybody taking the time. Thanks also to SIWEM, to Engineers Ireland Civil Department, and also the Water and Environment Department for organising it tonight and for providing the lovely venue. Now I'm going to speak for 15 minutes, just covering an overview of what we mean by integrated catchment management and looking at different sources of flood risk. So I'll speak for about 15 minutes or so before passing over to Mairead. We will look at two case studies, looking at Tralee CFRAM study and looking at the Exeter Surface Water Management Plan. And again, that's with the context of integrated catchment management. Before finally passing over to Colin, who will look at the challenges based on his experience in the UK sector. Now, we agreed to give this presentation back in October time. It wasn't quite as topical as it is now. It wasn't very difficult, sadly, to find these images. A lot of areas, a lot of properties, a lot of people affected by flood risk, both in Ireland and the UK. And importantly, they're from different types of flood risk, different durations, different times, and different locations. I get asked an awful lot as somebody who deals in the flood risk sector, is this a one-off? Is it a cycle? Is it unique to Ireland? Now, it's a very pertinent point, difficult point to get to the bottom of, but I found this slide which I thought was quite interesting. Now, it dates back to 2008 and looks at the decade before. And this certainly demonstrates that Ireland isn't unique, that flood risk is a phenomenon throughout Europe. And the interesting thing about this is that since 2008, that Ireland has quite a light shade of yellow there. If we were to update that to take effect of the flooding that happened in 2009, it happened in Dublin in 2011, the coastal events in 2014 out in the west of Ireland, and then of course the recent flooding has happened nationwide at the end of 15, beginning of 16. That colour would be a deeper colour of red, but it isn't something that's unique to Ireland. It's something that is pan-European. And this provides a bit more context as well in terms of the damage caused by flooding. Over that same period, 98 to 2009, that flooding has caused more damage in Europe than any other natural hazard. That sets the context of flooding generally. Now, whenever we talk about flooding, for this exercise we're looking at 6 different sources of flood risk. The first and the most traditional, I suppose, would be the river fluvial flood risk. And that's when watercourses or rivers become overwhelmed with the flow within them. They spill into the floodplain and impact upon a series of receptors. Second would be coastal flood risk, and that's flooding from the sea, typically low atmospheric pressure coinciding with a high tide, and that can cause tidal surge. If there are flood defences in place, then those are typically overtopped. This is the type of flooding that took place at the beginning of 2014 around the west of Ireland. Sewer drainage flood risk would be the third, and that's when the drainage system becomes overwhelmed with the heavy rainfall, or there's a blockage in the system itself, causing surcharge and ultimately flooding. Fourth would be pluvial flood risk, and that differs slightly from the drainage, and that's the flooding that takes place prior to entering the drainage system. Typically it would happen in low-lying areas and would happen above ground before it enters the drains. Groundwater flood risk, that's something that Galway would be experiencing at the minute, where you have the groundwater levels are rising above the surface water adjacent to it. Now, interestingly, because of the karst system out there, that although the water system in the river network is reducing, there's still a significant flood risk to those areas from the groundwater. And then finally, a reservoir flood risk. Now, this is where reservoir levels rise above their impoundment level, and the embankment itself would be overtopped, and then ultimately could be breached. And in terms of risk to life, if that happens, that would have the greatest impact. The overtopping of the impoundment dam would ultimately lead to breaching. So if we look at the 6 different sources of flooding, even though they're different sources, in terms of the receptors that are impacted, the options that we look at to manage that flood risk, how we would assess their viability, and ultimately the sourcing, the funding security, they're very similar. So you can see from the left-hand side here, although we have different sources, the receptors themselves are similar in that properties, roads, airports, schools would be impacted by the flooding. The options to manage them would be similar: storage, increased conveyance, diversion, pumping. How we assess the viability of them: are they technically viable? Environmental impacts, are they affordable? And the social impacts that need to be assessed. And then the issues regarding securing the funding would be the same. So availability of funding, priority, which scheme would you prioritise over another? And then you have the umbrella of government and political influence above that as well. Now, before we move on to what we are defining as integrated catchment management for tonight's presentation, traditionally what has happened is that each of these sources would have been appraised independently. So you would have taken, looking at the fluvial flooding, it would have appraised independently from the sewer flooding and similarly from the reservoir flooding. Now, the reasons for this independent appraisal of flood risk sources would include that different agencies would have different responsibilities for flood risk. So in Ireland you would have the OPW would have an influence, local authority, Irish Water, ESB, and then you have private landowners and private companies as well would have a responsibility for flood risk. And each of those would have their own funding streams with their own internal approval systems. And they also, for the different sources, would have different acceptables design standards. So for example, a drainage network would have a 1 in 30 year, whereas a reservoir would have 1 in 10,000. So there are a number of reasons why we have traditionally gone down the independent route. And again, following on from that, we have limitations in software, and that's something we're touching on tonight, is the changes in software, how that's allowed for a change towards a more integrated approach. And with software, you have availability of data sets. So each of the agencies with responsibility have tended to gather data within their own sector and interested in looking at options only to manage their own source of flooding. But if we could move away from that, if we could, we're very much on a journey, and integrated catchment is a journey. And where do we want to get to? Well, ultimately where we want to get to is that regardless of the source, if we could pull all the sources together and look at all the receptors that are impacted from the different sources of flooding, could we appraise one option or 2 options to deal with all those different types of sources? They'd all be assessed as a single entity, and the funding could be pulled from the different agencies so that we have one funding stream, one option managing more than a single source of flooding. As I said, we're very much on a journey, and the OPW, for example, they already deal with fluvial and coastal, so they do deal with more than one. And in the UK, through funding from through DEFRA, central funding from DEFRA, you have local authorities who would look at, in partnership with the Environment Agency, would look at sewer flooding, fluvial flooding, and pluvial flooding. So we're very much getting there. But if we could move forward and have a fully integrated management approach, the benefits of it would be an improved standard of protection, not just at a town level or a street level or individual property level, but we could look at catchment benefits. We could look at an increased collective standard of protection for those areas, for towns and villages, as well as the individual street. And a more sustainable option. But ultimately it would come down to value for money. I mean, that would be the ultimate carrot. I'm just going to give, to reinforce the point of what integrated catchment might look like, I'm going to use an example for Tralee, and this is very theoretical for all the environmental scientists in the room. We need to park that for the time being, that aspect of it, and park the cost. We're looking purely at a theoretical exercise here. But Tralee is at risk from 4 different sources of flooding. It's at risk from fluvial, coastal, sewer, and pluvial. Now, if we were to go down the traditional route and appraise each of those different sources independently, we might be promoting flood walls to manage the coastal flood risk. We might be looking at pumping stations to manage the sewer drainage flood risk. Increased culvert size might be needed for the manage the fluvial flood risk. And then a streets of streams concept where you're conveying flow down the street into managed areas as part of the fluvial flood risk. So if we were following a traditional approach, that's possibly the type of solution that might be promoted. Now, if we were to look at a fully integrated catchment management approach, an option that might be promoted that wouldn't necessarily be promoted under the independent approach would be a tidal barrage. And this is where we have to park the environmental aspects for this exercise. But if we could promote a tidal barrage, what it would do is it would reduce the coastal flood risk straight away, but it could introduce capacity within the drainage network in terms of tide locking, introduce capacity into the fluvial network, and ultimately then it would give more capacity to discharge fluvial flood risk into both the drainage network and the river network. So a tidal barrage would possibly be too costly to promote as a single source, but if we could work towards an integrated catchment management approach, something like that could be viable. So as I was saying, we're very much on a journey. And one aspect we're going to speak about tonight, and Maid will touch about this, is how developments in the software and developments in data that we've collected are allowing us to move along that path, that run times and tools are available now to allow us to collect the data, to do the runs, to start looking at an integrated catchment management solution. It's something that the government funding agencies and the private bodies and the funding bodies that are involved in flood risk and are impacted by flood risk, that they certainly see the advantages of it. But it's not without its challenges and risks. And that's something that Colin will talk about later. So that's a brief overview of what we mean by integrated catchment management. I'm going to pass over to Maria now, who will look at 2 case studies for the Tralee, CFRAM, and also the Exeter Surface Water Management Plan.
Good evening, and thanks very much for coming along to our presentation. For my part of the presentation, I'm going to take you through case studies of 2 projects where we applied an integrated catchment management approach and built hydraulic models using Innovy's ICM software. The first project is for the Northbrook catchment, which is in the city of Exeter. It's on the southwest coast of the UK. Here we were commissioned by Devon County Council to carry out a surface water management plan. To understand the surface water flood risk in the area, we needed to build a hydraulic model that would describe the mechanisms that resulted in the surface water flooding. The second study I'm going to look at is the Tralee CFRAM study. This is part of the CFRAM, the overall CFRAM project, which is commissioned by the OPW. And here we are looking at the interaction between the coastal and the fluvial flood risk in Tralee. And we used the ICM model to determine that. Throughout my presentation, I'm going to give you a summary of both these projects. I'm going to discuss how we applied an integrated catchment management approach and discuss the sources of flood risk examined. I'm then going to outline why we used Innovy's ICM software and the benefits and the lessons that we learned through these projects. The first project is the Northbrook catchment. How this came about, it started from an initial preliminary flood risk assessment that was carried out by Devon County Council on the entire county of Devon. It identified the requirement for a surface water management plan for the city of Exeter. Further to that, a strategic surface water management plan was carried out in the city, which identified wet spots throughout the city. One of these wet spots was in the Northbrook catchment. The Northbrook catchment is 12 kilometres squares in size. It's a relatively steep catchment. Over its 2 kilometres in length, there is a fall of 100 metres. It's also a very urbanised catchment with some green park areas. The main watercourse in this catchment is the Northbrook watercourse, which flows from north to south and flows into the River Exe at the downstream extent of the catchment. This study was commissioned by Devon County Council, and they are responsible for the surface water flood risk. The River Exe, which is a main river which flows through the city of Exeter, is the responsibility of the Environment Agency in the UK, so it was not considered in the study. There has been records of historical pluvial and fluvial flooding in the Northbrook catchment. Understanding surface water flooding is a complex due to the flooding sources and the mechanisms. And in the Northbrook catchment, we had 3 sources of flood risk which were contributing to the surface water flooding. This is pluvial flood risk, the sewer drainage flood risk, and fluvial flood risk. We needed to understand the surface water flooding and the mechanisms of the surface water flooding in the catchment. We needed not only to look at these individually, but we needed to look at the interaction of these on each other. And to do this, we used Innovy's ICM software, because this enabled us to include these 3 elements in one model. Over the next few slides, I'm going to describe how each of those mechanisms was included in the model. The first of these is the pluvial flood risk. To understand the pluvial flood risk on the catchment, a rainfall hydrograph was applied onto the catchment. The catchment in the model is called the 2D domain, and it is informed, the topography of the catchment is informed by LiDAR, which was inputted into the model. Flow, or rainfall, when it hits the catchment, flows through the catchment by gravity. And in order for the model to calculate this, it splits the catchment up into several mesh elements, as you can see here. Flow travels from one mesh element to the next. So at each mesh element, we have 2 calculations being carried out at each boundary. That's the flow into the mesh element and the flow out of the mesh element. So at each mesh element, for one time step, we have 6 calculations being carried out. The mesh varies across the catchment. So when we have built up urban areas, we have a lot more with smaller mesh elements. And this is in order to understand the complex flow paths that occur in built up areas. However, as we get out to rural areas where it is flatter and the flow paths are much less complex, the mesh elements are larger. This is a unique feature to the Innovy software, and it's quite key into how we look at integrated catchment management. Model run times are dependent on the number of mesh elements in a model. Therefore, the more mesh elements, the longer the model run times. This is really important when we're talking about models that could take greater than 24 hours to run. Innovy software allows us to model entire catchments and looks at the broader rural areas in less detail, and while capturing those complicated flow paths through the urban areas. The sewer and drainage flood risk was also included in the model. In Northbrook, we had 3 different drainage systems. We had the storm system, the sewer system, and the combined system. We obtained information from these systems from Devon County Council, and this was input into the model. When the flow was flowing across the 2D domain and it hits a gully or a manhole in the model, flow can enter the drainage system. The rate in which the flow enters the drainage system is determined by the capacity of the gullies and the depth of water above the gullies. Once flow enters the system, flow is calculated going through the drainage system using pipe flow equations. When the drainage system becomes surcharged, we can get overtopping of the manholes and the gullies out into the 2D domain, and this flooding will take an overland flow path in the model. If we have sealed manholes, these can be represented in the models, and this characteristic will be disabled, so the flow will not be able to go out into the 2D domain. Flow can also flow from the drainage systems into the watercourses. The watercourses are included, so the Northbrook watercourse was included in this hydraulic model. The model was informed of the topography of the watercourse by cross-sectional survey data at several cross-section locations. And the channel flow is calculated using open channel flow equations in the model. When the water levels increase above bank level, flow will leave the water channel and enter the 2D domain, where the overland flow path is modelled. When overland flow paths hit the bank of the watercourse, flow can go into the 1D element of the river. Flow can also come from the drainage system into the watercourses and back up into the watercourses if water levels permit. All the structures on the river, like the bridges and the culverts, are all included in the model because these are important as they affect the conveyance of the watercourse. So we have, to summarise, we have a lot of data in the model. And Innovyze ICM has a GIS viewer, which allows us to view all this information in plan. So we have our drainage systems, our watercourses, and the topography, the LiDAR. When we run the models, we can also view the results as they flow through the model, and this helps us understand the flow mechanisms. I'm going to take you through an animation of the results in an area in Northbrook. So this takes us through the entire rainfall event, and at the initial onset of the event, you start to see these overland flow paths and localized ponding in this low-lying area here. This path develops as the watercourse overtops in this location, and the overland flow path, the flooding on this overland flow path increases, flooding this road and eventually back into the watercourse. Over here we have another flooding mechanism, which is an overland flow path into a low-lying built-up area. But when we further interrogate the model, we can also see that some of this flooding is contributed to by overflow from the manholes in this location. These flow mechanisms are important and help us inform the flood management measures that we might consider for these areas. For example, where this overland flow path was, we couldn't just treat the overland flow path in isolation because we also have flooding coming from the drainage system. The model, along with informing us what flood prevention measures are viable or suitable for the area, it also helps us inform us which ones are viable. The resulting flood depths can be used to inform the damages of the flood events and can also be used to identify the receptors at risk of flooding. In Northbrook, it was identified that in the 10% AEP event, which is the flood event which has a 1 in 10 chance of happening in any given year, there are 42 properties identified to be at risk of flooding. In the 3.3% AEP event, which is the event which has a 1 in 30 chance of happening in any given year, there were 139 properties identified at risk. And in the 1% AEP event, which is the 1 in 100 chance of happening in any given year, there were 269 properties identified at risk. So the model identifies the receptors and gives us an indication of the mechanisms that result in the flooding. For the Northbrook catchment, there were 4 areas where viable options were considered. The options that we looked at here were for the 3.33% AEP event. I'm just going to talk you through one of these options, which is a combination of measures for the heat tree area. Here there were 2 flow paths, one from the heat tree playground here across onto the residential, to the built-up area. To reduce this flow path, we looked at a storage area in this location, which would stop the flow, the overland flow path here. We had another flow path from the Northbrook watercourse as it went into a culvert. This culvert was undersized, So we had significant out-of-bank flooding upstream of the culvert, which took an overland path through the built-up area to the downstream extent. Here we applied the streets as streams concept, where we looked at attenuating as much flow as we could in order to reduce the flow coming out of bank. This flow was maintained on the streets, and we raised curves in areas to make sure it stayed on the street until it could be diverted downstream to the downstream extent of the watercourse. Here we also needed to apply individual property protection to some of the properties, and this would be floodgates at thresholds, just to prevent the water coming into the properties. I'm going to take you through some of the lessons that we learned from this project. When we started on this project, Innovi's ICM software was in its infancy, and we were building up our capabilities in the use of it. We found that the development of the mesh at the initial stage in the model was causing us some problems. The mesh was becoming too detailed in the urban areas and detailed beyond the level of detail that really was required. We found that we looked at the data that informed the mesh, which is the LiDAR data and the land use mapping data. And we found that if we applied simplifications to this data in GIS prior to the inputs into the model, that it reduced those problems, eliminated those problems, and the mesh was an appropriate scale for the required flow paths. The next study I'm going to talk to you about is the Tralee study. So this is carried out as part of the CFRAM study. And for those of you who don't know, the CFRAM study is a catchment, flood, risk assessment and management study. And it looks to address the fluvial and coastal flood risk in 300 towns in Ireland. Tralee is one of those towns. Just going to describe the catchment that flows through Tralee. So, let's see my mouse there. The River Lee is the main watercourse which flows through the centre of Tralee. It has a catchment the size of 98 square kilometres. It's also a tidal watercourse as it flows out into the Atlantic Ocean just downstream of the Shannon Estuary. The tidal influence extends significantly upstream, and it can be shown by that green buffer on the schematic. We have several watercourses flowing into the River Lee, which flow through the town of Tralee. We have the Mackey's Channel and the River Big. These are both urbanised channels and have been culverted for an extensive length of their downstream reach, which can be shown in red there in the schematic. The Mackey's Channel some of the flow from the Mackey's Channel is diverted across to the Big River, and some of the flow from the Big River is diverted across to the Rathass area. This was part of a flood alleviation scheme, which is about 30 years in place at the minute. When these diversion channels were originally constructed, the Rathass area where the flow is being diverted was a rural area, but it's now a built-up area, and there is flood risk in this area. The tributaries to the south take runoff from the Sleevish Mountains down into Tralee. As we have a significant tidal influence extending upstream into the River Big, we needed to model the whole of Tralee as one model. We couldn't cut it up in half because we needed to be able to understand the full effect of the tidal influence on the fluvial flood risk, and vice versa, we needed to be able to understand the influence of the fluvial flood risk on the tidal flood risk. So this really comes down to why we used Innovi's ICM software for this model. When the CFRAM process started, ICM was in its infancy, so it wasn't one of the softwares on the specification. So we had to seek permission from the OPW in order to use the software for this model. But the main driver behind that was the model runtimes. This is quite a large area to be included in one hydraulic model. And if we had used the software that we had been using on other studies in the CFRAM, the model runtimes would have been in the order of 48 hours. Now that might not seem like a big deal, but when you're building a model and when you're initially running the model, you always get instabilities in your model and you have to solve those. And it's an iterative process. So the longer the model runtime takes, you're going to lose momentum in solving those problems. Now, while that may seem as a problem just for the consultants, the model itself becomes a key deliverable of the project, and it is the OPW are going to own that, and it could potentially be used by Kerry Council in the future. And a model that takes longer than 48 hours to run is just unsustainable. Whereas Innovai's ICM, because of the flexible mesh, allowed us to run these models in 16 hours instead of 48 hours. Another feature of the Innovai software that was one of the reasons we preferred to use it for Tralee was the long culverted watercourses. The other software that we were using doesn't deal well with culverted watercourses, whereas Innovai's was more robust in this. I'm just going to talk briefly about the mechanics of the model here. The fluvial flood risk, the watercourses, were modelled in the same manner as I explained in the Northbrook model. However, instead of applying pluvial or rainfall event to the entire catchment, flow hydrographs were input to the upstream extent of the watercourse. These flow hydrographs propagated through the channels, and out-of-bank flooding occurred in low-lying areas, and the overland flow paths were represented across the 2D domain. When we ran our fluvial events, we applied a tidal boundary to the River Lee. This allowed us to understand what influence the backing up effect from the tidal boundary had on the fluvial risk. When we were looking at the tidal flood risk, we applied a tidal boundary to the 2D domain that was touching the sea effectively. When the water levels in the tidal boundary were above the ground levels in the model, we had overland flow paths propagate inland. And when we ran the tidal event, we ran a flow down the River Lee so we could understand what effects the discharge from the water course had on the tidal levels. The results from this model are shown on the scheme citation. The results in green show the flood extents for the 0.5% AEP coastal event, which is the coastal event which has a 1 in 200 chance of happening in any given year. The blue results there show the fluvial flood risk, and that is the 1% AEP event that's shown there. As you can see, there are a significant number of receptors in Tralee at risk of flooding, and these flood extents have been used to, or are currently being used to inform options to manage this flood risk. In this area here, we have an interaction between the fluvial and the coastal flood risk. So the coastal flood risk is on top of the fluvial flood risk, but there is risk from both elements in this location. When we are developing options in this area, we need to develop options that will protect against both the coastal and fluvial flood risk in this area. This takes me to the end of my presentation, but just to summarise, I've talked through how we've applied an integrated catchment management approach in Northbrook catchment by looking at the different sources that result in the surface water flooding. And I've talked about in Tralee similarly how we've looked at the coastal and fluvial flood risk and their impacts on each other. Really, I suppose the point that I'm making is that the developments in Innovai's ICM software has allowed us to carry out this integrated approach when we come to the modelling. 6 years ago, it would have been really difficult to carry out this work because model runtimes would have been prohibitive. I'm now going to pass you on to Colin Horn, who's going to talk to you about the experiences and challenges in the UK water industry from his experience over the last few years. Thanks.
Well, good evening, everybody. Probably drawn the short straw, getting the last slot. Well, I think it's probably the easiest one because there's actually no defined process I'm going to go through, and it's all very conceptual. Probably raise more questions than it will answer, and it's probably not the only way going forward as well. There's not a great deal of slides or presentation I'm going to go through over a fairly relatively low key. And it's all based on my experience over the last 25 years working between government bodies and private bodies as well. The way forward will develop over the next few years, and maybe we might come back to present that with the experiences that we've got going forward. Just a bit of quick background as to where we're going with this and where it all comes from, where it stems from. It all stems from the initial modelling, focused mainly on from sewer rehabilitation modelling in the 80s, 90s. That was very focused on very just isolated catchments because of the modelling capabilities that were around at that time. And it still contained elements of water quality. It still contains elements of structural and flooding issues associated with it. So it still broke it down. It still understood that we still had those issues then. So this is something that isn't relatively new, but we've now got much more better modelling tools to take us forward. The second phase went into more looking at water quality, and that was more driven by the urban pollution management type approach and the impact on receiving water courses, again because the actual software developed that capability going forward. Other water companies used it more as to go from a snapshot approach of the SRM through to more a live dynamic approach where we looked at incidents occurring, what interventions were required from that, and understood the changes that were happening through the lifespan of that catchment to actually respond much more quicker effectively. And we're now going into this latest stage because of the ICM capabilities now within the software that's been developed by Innovise that brings in water quality, brings in the river, brings in the local sewer network, etc. in terms of that. And that's also now being driven by Ofwat, which is the UK water regulator, that looks at, and they've provided a guideline document, which is the Drainage Strategy Framework, which is equivalent to the drainage area planning that's undertaken by Irish Water. And that's understanding that this solution needs to be approached by all bodies now, not just individual stakeholders in there. In itself, that brings a lot of challenges, it brings a lot of constraints, and it brings a lot of risk associated with that. It's quite a bold initiative. It's been driven by a lot of the recent flooding from 2004, 2007 onwards, but nothing's really moved forward at this moment in time. And I think the regulator and the government bodies have seen that and are moving that to make the water companies and the government bodies act together. So that's why they've delivered this document to help drive that. But really, what is ICM to each stakeholder? That is different for each individual stakeholders. You go from the river management side of things, they're looking at the bigger regional picture, they're looking at water framework directive, they're looking at river basin strategies and that type of approach. The urban management is more looking, which contains the water companies and the local authorities, looks much more contained to one locality. So just that urban catchment. So again, you've got a mismatch there straight away, that one body is looking at a big regional picture, some bodies are looking at very much self-contained elements of work, and how do you bring that all together? There's also then looking at the integration of the software tools and the alignment of model build and design specifications. For instance, the local authorities more often than not use microdrainage. The water companies, they tend to use InfoWorks or Innovise software. Each has its own model build specification. Also, they have their own different ways of looking at verification and calibration of those models. So everything is different. It all needs to be brought in and aligned. And that's going to be exceptionally difficult to do. Also the design specifications, the air or the water, rivers, people look at different aspects in terms of what they look at for their runoff as opposed to what's looked on an urban catchment. So again, there's a lot of complexity and negotiation to understand how these are all going to actually work together. Following on from that, we've also then got the risk of what is a benefit analysis. Each individual organisation has its own risk allocation, has its own benefit analysis. For instance, one of the water companies, they don't actually use amenity value of the receiving water course in terms of what the air look at as a benefit to what their scheme is. It's of no interest to them in many ways in terms of getting capital funding. Approaches to surface water removal and operational integrated schemes. How does that actually work? How are we going to remove the surface water inputs from there? Where do we put them? Do we have swales? Who looks after suds? So there's lots of issues associated with the management of that and where we're going. All needs to be resolved. The management of swales has been ongoing for 10 years that I know about, effectively, who would manage that solution. Therefore, the water companies don't actually look at that as a solution. So we have to cross that bridge. Is there some open space available that we can actually divert that excess flow into? Who would purchase that? Is that going to be CPO under the local authorities? Where do we get it from? Lots and lots of issues associated with how this is actually going to operate. And then we go on to, well, how is the capital funding actually associated with that? And in terms of operational management, where do we look at the assets of that in terms of who manages those assets for certain, where we've done an integrated solution? How is the split of operational costs going to be allocated? Significant challenges, constraints and risks associated with it. So it's very easy to actually put in a body and a guideline, you will do this. To make that actually function, it's probably going to be a couple of years worth of negotiations and discussions. So what we've been looking at is, and this is purely conceptual, looking at that, that's just a very typical catchment where we've got a couple of rivers running down through there, effectively going out to sea with a tidal influence there, and looking at each of the individual catchments that come into it. So again, very siloed. The earth people look at the bigger picture, whereas a couple of the other stakeholders will just look purely at each of these locations and look at what issues they've got in those locations. Now there is a slight problem with that, and there's a slight error on there. We could actually have a river running through the catchment, which is not on there effectively. But what we're looking at now is how we integrate the software and how we can look at understanding the impacts of the river on the catchment and vice versa. So what we're looking at effectively now is to actually define boundary limits upstream and downstream of connection points from those catchments. And each of those boundary points will be considered to look at no change to that river flow, or it would look at reducing that river flow so it removes the risk to flooding of properties. And the next phase would then be to look at the reduction of river flow to remove the risk of flooding to properties flooding and flooding of land. And actually from that scenario, for those different scenarios, we can pull out that area and put that into the ICM software and then look at the solutions within each of the catchment based on those boundary conditions. And that would then give us a matrix of options based on the river flow conditions. Now, that would then allow us to understand what the variation would be in terms of scheme sizing, project sizing, and impacts on there. Likely that would be potentially an iterative approach between the various organisations. It can still be done, and the modelling can still be done individually in the silos, but the impacts can still be discussed with all the stakeholders going forward. That will then provide us with looking at the benefits and risk allocation. So each individual stakeholder will have its internal approvals and its benefits and its risk assessments, and you're never going to change that. They will have to please either government bodies or shareholders or whatever, and it's going to be very difficult to do that. What we're looking at is pulling that out into what would be an ICM combined approval and benefits and risk, and allocate the funding split based on those benefits. And one of the issues we've got from Exeter will be looking at, instead of looking at the return period as a design solution, and it's something that we probably need to get away going forward in terms of benefit and design, is how many incidents are reduced by each individual scheme. So it could be that we could actually identify the actual allocation of funding split on the incident reduction for that element within the catchment. Now, for an example, we're looking at stakeholder 1, which could be, here we've got the OPW or the AA equivalent, and looking at Tralee, that in terms of putting a barrage on there, the benefit to there would be reduction in flooding of the fluvial nature. Stakeholder 2, which is Irish water, it could be a reduction in the sewer flooding because of the removal of that barrage. It removes certain scheme sizes. It could actually be a less of a scheme that's required. And also then for the stakeholder 3, which would be Kerry County Council, that would look at storm drainage, again, which could be reduced in size because of the barrage effectively on there, and it could also reduce the impact of pluvial flooding. So effectively, to do that one element of putting the barrage in, you could redistribute the costs associated across those 3 stakeholders based on that type of benefit in terms of incident reduction. Something that's going to be exceptionally difficult to do, and work is ongoing looking at how they can look at that combined benefits and realisation within the water companies and within the various stakeholders in terms of that. The whole benefit of this is going to almost rely on funding around a scheme from all of the stakeholders and what's going to be most equitable to do that. And going forward, it may well be that the actual drainage strategy framework is going towards network management, and a lot of water companies now are looking at how they can manage their network, and a lot of them are installing monitors within the system looking at CSO spills and various other aspects in terms of operational performance. Now, looking at there, we could have monitor 1, monitor 2, monitor 3, monitor 4 that are in there. Monitor 1, there we go. We'll be looking at the flows and depth, etc. within the main river. Monitor 2 will be based potentially on, say, a surface water input into the system that we would like to remove, but the impacts of removing surface water from the system could have a negative impact on the operational performance within that catchment. Silt build-up could actually increase, which could actually give us a problem with sewer flooding from other causes. Monitor 3 could be actually based on a CSO spill, or it could be actually based on a DG5 attenuation tank to solve flooding. And monitor 4 is based on a local watercourse rather than a main river. So, for example, you could be actually looking at the monitor 1 levels, and we could actually be diverting flows into that main river from monitor 2. So we're removing the impact on sewer flooding within that area. But it may be that as the river level rises, we actually may increase fluvial risk. So it could actually be that we actually control that, say, right, we're going to stop the flow from going into the main river, and we're going to put it back into the sewer. The benefits of that will be that we maintain the sewer flushing, so we get rid of the silt. So we could potentially still have a reduction in risk to flooding from other causes. As the river level falls down, we could then open that flow path back out into the watercourse again, effectively. So we're monitoring that aspect. Now, at monitor 3, we could be looking at CSO spills or storage within an attenuation tank or storage at the CSO. And it may well be that as the water level rises in there, the system becomes more dilute, which means we could actually increase the spill from those locations back into the surface waters, back into the local watercourse. And that actually then may help by removing the level of storage in that storage location, which would allow for any future storm event, follow-on storm events, and create a little bit of capacity to help him actually improve the spill from that location as the river falls later on, or actually remove the risk of the sewer flooding from that perspective. So looking forward, it may well be that the actual drainage strategy framework becomes linked much more into network management approach, and that covers both river and urban areas. So that's something that is potentially being looked at, and that's a long way down the line. So really summarising where we're at, the impact of flooding is a significant issue, and it's from all 6 flood sources. The majority is obviously coming from fluvial and sewer network in the vast majority of cases, but 6 flood sources are still important. We are historically still looking at independent silo appraisals for each of the flood sources, and that's something that will take a lot of work to actually get round to understand a fully integrated catchment approach and a network management approach. It's something that is a target going forward, and it's been a target going forward probably for about the last 10 years, and we're still getting there. So it's not something that's going to happen overnight. It has been identified by all the funders, all the government agencies, that going forward, the incidents and flooding we've seen over the last few years needs a much more integrated catchment management approach, and it's got to involve all stakeholders, not just one individual. And looking back from what I've just described there are significant challenges and there are risks associated with the ICM approach. It will involve a lot of hard negotiations, a lot of alignment between the various systems, between all the stakeholders going forward. The presentation that you've had shown an overview from Peter, it's shown a detailed approach from Mairead, and it's got some conceptual thoughts that we're going forward with. And it isn't the answer to everything. It will need an awful lot of work from all organisations, and that's all engineers in this room as well. And thank you for that.
Okay, I just want to thank the speakers very much, and what we're going to do now is we're going to try and have a Q&A. We have a microphone here for the benefit of people, of those watching and listening online. What I'll do is, if I'd ask you to put your hand up, and if you wait for the microphone, and then when you get a chance you could identify who you are and maybe give your speak or your question using the microphone. So is there any volunteers over there?
Thank you very much. That was a very interesting presentation. John O'Sullivan is my name. I'm from UCD, and I have a question for Mairead. And it's the comment on the calibration process and the data requirements for calibration in the 2 case studies that you presented.
Thanks, John. The calibration for the extra study, when we were looking at the surface water management and the surface water risk, we ground truthed the information. So we identified the flow paths that were there. Well, we didn't have a lot of data that we could use, the hard gauge data that we could use to calibrate the model. So site visits were carried out after we looked at the model results to see if the flow paths and the mechanisms of flood risk would actually happen. And in certain areas, we had to refine the model, and in certain areas, we found that the flow paths were correct. And that's really how we calibrated that model, but it wouldn't be calibration as you would technically call it. It'd be more like verification. In the Tralee model, as with all the CFRAM models, we generally, ideally, looked to carry out 4 calibration events. Now, a lot of the catchments, we didn't have, again, the hard data. And I can't just off the top of my head remember what happened in Tralee, but I do know in a lot of the cases in the CFRAM study, we really had to carry out ground truthing again and look at the flow paths to see did they make sense, were they sensible. We also had a consultation process where the maps were shown to the public, and people in the area who had knowledge of historical flood risk did offer opinion at that stage. But as in terms of calibration, ideally we would like to calibrate against 4 historical events, but it's not always possible due to the limitations in the gauge data. Does that answer your question?
Yeah, thank you.
Thanks very much. Question from Mairead again. My name is Jerry Mahan from IE Consulting in Carlow. Is it valid in the models to, even though there may not be a groundwater contribution in terms of flooding, to ignore groundwater in the model because it could still be contributing in terms of either infiltration into your network, or equally the variation in soil conditions could be a cause for maybe infiltration in areas where you wouldn't expect it, and also maybe limiting infiltration in other areas where you might expect it?
Yeah, so groundwater wasn't expressly considered in either of the models. We did, in the Exeter case, the ground conditions were considered. So we did have the land use mapping, which informed the different land types throughout the catchment. And when we applied the rainfall to the catchment, there was initial losses due to groundwater and losses into the ground. So for hard standing areas, you would have no losses, but for green areas, you would have losses. In terms of infiltration into drainage systems, that's not expressly modelled in any of the models we have, but it is something that does need to be taken into consideration when we look at flood risk in the areas. Okay.
Question for Mairead again. Sorry. My name is Nasfin. I'm from the Palace Wire Consulting Engineers. In relation to the quality of the information you get from modeling you, did you get a chance to compare them with some intuitive or simple models, whether it was worth spending 16 or 48 hours running the models?
Sorry, can you just repeat that again?
What I was saying is, like, we have a number of other models which we use to generate the same output you have just used. Mm-hmm. So did you get a chance to compare your model results that they were actually superior to the ones that are available out there?
Well, we didn't expressly model those catchments using other software again. I suppose you're trying to say the comparison between the different software models and the results that they have. We have looked, because when we started using Innovi's ICM software, we did want to make sure that the model results were sensible. And when we finish a model, you do always have to examine the results you always have to carry out diagnostics on the model to understand there was no mass balance errors. So that's when you're losing flow throughout the model. We did find that across the grid in the Innovi's software that we were getting less mass balance errors than we would traditionally in other model software packages. Now that may be just, sometimes that can be luck on the model that you're doing, but we have used this software in a number of projects, and that's, I suppose, the general feeling from the modelers who are working with that software package and other software packages. But I suppose to answer your question directly, no, we haven't looked to compare if we model this catchment using other software and ICM and what were the differences. No.
Yeah, just to add on what John said, because we didn't go through that calibration to really hard data.
Mm-hmm.
Probably not that easy to compare your models and doesn't with the output of your model. That's what I highlight.
Mm-hmm. Yeah.
maybe add that as well. I mean, what determines the run times tends to be the size of the mesh that you choose, and you have to fast. If you're short on calibration verification data, it's important to look at the purpose of the model. Is the model to produce maps, or is it to produce a strategy? Is it to produce detailed design? And that can influence the size of mesh as well. If you know it's going to be used for a detailed design, construction is going to site straight away, you might choose a finer mesh at that stage to make sure that the model is more accurate, that the heights of the walls or the storage area are going to be more refined. Whereas with the more catchment-based approach, and you're looking at more strategy, you might take a more loose grid cell size, a larger grid cell size, which would reduce the run times. So it's very much a balancing act between how much detail do you need for the model, how much data do you have available, as well as what the need of the model is, why you're developing the model. So all those factor into the runtime.
Mr. Fee in GMS, congratulations to all the speakers. I have a question for you, Colin. So, first of all, thanks for the presentation. I don't have a background in water, but I'm fascinated by the ICM and the difficulties in getting that approach across. You said it's been ongoing for the last 10 years. It seems, from an engineering point of view, obvious that the agency should be taking that on. I wonder, could you talk in a little bit more detail as to why there is such a difficulty? Is it, do you feel it's a silo approach? And why, for example, if you tasked one of the agencies explicitly with having a mandate to look at ICMs, that's something that could be done. So just interested in why an obvious thing is taking so long.
I think politics comes into it more often than not. I think looking at it, the engineering sense is there. It's the obvious thing to do. And going forward, or historically in the past 10 years, having, from my perspective in terms of the UK, you've got the regulators, which are obviously regulating the water companies and setting some of the standards, etc. And then for them to be involved in actually determining a scheme and setting that funding around, it's almost a little bit too difficult for them to come to grasp with. So it's very hard for them to split the function between regulator and working together to actually deliver a solution. I think there's a lot of that into it. That's why I said there's going to be a lot of negotiation to get around that gambit to say what's best for the overall customer within that environment to stop the flooding occurring. I think the last few years that is driving it that way because of the frequency of flooding. You know, the customers are getting fed up of being said, well, you flooded because it's a 1 in 300 year event, and yet that's occurred 3 times in the last 10 years. So I think now there may be a drive to get around that political issues associated with working together to get a fully functional system where the funding and allocation of funding is spread across everyone to understand the benefits to all the organisations. At the end of the day, it's the same customer that's paying and being looked after by the government bodies as being looked after by the water companies. It's all the same people. So why are we not addressing it as the same benefit to all those people? And that's why I was looking at getting away from a design return period to looking at the incident reduction. And one of the drives in the latest cycle determination for the water companies is to look at functionality of reducing incidents for that as a target for them to do, so that the mechanisms are being put into place slowly to allow that joint approach to occur. But it's going to take a few years to sort out. Does that answer the question? It's a difficult one. It's a very difficult one. And engineering doesn't come to the forefront when politics and organisations and private companies are meeting around the table in many ways.
So if I can have a follow-up to you, who do you think should be implementing this requirement to have in an ideal situation? Are you talking about David Cameron?
It's at the moment it's being set really between DEFRA and the EA. That's where I think that's where it's going to be driven to them to drive effectively, looking through the water companies, the local authorities, the land drainage authorities, and the way we're looking at is almost getting a body that will look at a catchment, and we're looking at a concept of how it's going to work in terms of that and getting those people on board. And we've had a couple of workshops to look at that and drive that to drive away the traditional way of looking at it. And they have actually gone down reasonably well, to be honest, between the EA and the local authorities. The last one involved was about 3 months ago, and it did actually go really well, and they're understanding from that perspective, but it didn't involve anybody from the regulatory side of it as well. So once we start throwing that into the picture, then it may become a little bit more difficult and a little bit more fraught as to actually get sign up going forward. And there will always be internal approval procedures that you've got to go through to get that funding sorted. And there will always be a risk, and that's why we're looking at all the various scenarios. There will always be a risk that you won't be able to get funding from a particular stakeholder, which will impact on the solution.
My name is Paul. I just wondering if there seems to be higher incidence of flooding throughout the world, and the suggestion is that it's global warming. Is that generally accepted with you guys in this modelling? And does that mean that the parameters, design criteria, have to be increased? In other words, what may have been 100-year storm 10 years ago may now be a more frequent event, possibly. Can you just give a comment on that overall?
There's probably other people more qualified than myself in the room to answer the issue of climate change. I suppose all you can deal with is the data that's there. If you look at the data that's available, we're not blessed with hundreds and hundreds of years worth of data. We're only blessed with data that's some of it's 20, 30, 40, 50, if we're lucky, 60, 70 years old. General consensus would be is that we had a particularly dry period in Ireland over the 50s, 60s, 70s, 80s, 90s. Some of the work we've done in the Shannon CFRAM study itself, we do have 100 years worth of record. And if you look at water levels in the Shannon dating back to 30s, 40s and early 50s, actually there was quite a lot of flooding. But then it was dry. A long period of time, 50 odd years, was relatively dry. So when people say, I never remember this river flooding before, well, they're right. They just aren't old enough. If they were old enough, they might have remembered. But now we're definitely in a period now where it's wetter, wetter than it has been. I think science, with general consensus in science, is that global warming is here. Sea levels are rising, temperatures are rising, there's melting in the polar caps, and science is there to prove that it is happening. In terms of the return periods, I think that's the point Colin was making, is to possibly move away from that and move towards incidence instead of trying to determine a design period for a engineering solution. Maybe we look at what's affordable, or maybe we look at targeting areas that are at risk and looking at all sources rather than what's 100-year. If you look at what's 100-year event now, we used to say we don't go into another dry period, and in 20 years time you run the stats on it and you find out it wasn't 100, it was a 1 in 200. Or conversely, if it continues to rain, a 1 in 100 might turn into a 1 in 20. So very much a moving feast and a snapshot, and it's all stats.
Thank you, Suzanne Davis from Irish Water. Thanks for a very interesting presentation. Colin, your last, when you were talking about managing integrated management, you were kind of, maybe this time you'd switch a flow from here to there, or you'd let the sewer flood or whatever. And that's very interesting, and I can see how it would work in a small catchment. But I'm just wondering, in terms of the flooding we saw on the Shannon, in the last month or two, and if you had to manage every single catchment in the same manner with all the contribution to the Shannon catchment, is that really feasible? And on the scale of the flooding in the Shannon, something that would, would be greater than what you could control, even if you had a very integrated system. Thanks.
Yep. As I said as well in the presentation, we can't cover every extreme event in terms of that. That will, yes, look, it might well work in a number of smaller catchments. It might work in some bigger urban areas, which are isolated sub-areas within a catchment. But you're never going to be able to actually resolve all the big flooding issues that we've had, similar to what happened in December, etc. And it may well be that for those particular areas, in terms of risk management from that, you're never going to achieve it. You can't cost to do it. And it may be that you might need to look at some actual other form of making properties resilient to that flooding. So you're not going to be able to solve everything. And it will be horses for courses where you are. It may be that in terms of what you said there, with something we put in place, it might remove the risk of flooding properties from 1,000 to 500, but it's still beneficial. But for that remaining 500, you might have to do something entirely different, and that may make it more resilient. It may be that you put flood doors on there or whatever, or you lift the electrics up, or you put waterproofing plaster on or whatever, or you do something to stop the water going in there, but you might never stop, and you will probably never stop the water running down the road. Yeah.
Patrick McGill from Jacobs. This is Colin. Colin, I just wanted to make sure I captured this right, but it seems to be the big stumbling block at this stage now, scale. So certain people are looking for a macro scale solution, certain people are looking for the micro scale. And it seems to be just from your presentation that you the boundary conditions seems to be in the key to unlocking those two challenges, and the boundary conditions letting public bodies talk to each other in a sense. Am I capturing that right?
Yeah.
That's the lock to unlock?
Some of the ones, it may be that when you do the solution development, you might actually find there's no benefit on any of those stakeholders, and that one individual stakeholder has to fund everything, 100% of that scheme. It's just to look at the iterative process between what we can do with the watercourses and the impact and time delays and time difference between urban runoff and river runoff, to see if we can utilise some elements of storage within each of the networks effectively, which we don't really look at then.
Any other questions? Okay, I'd just like to express our thanks for all the detailed questions in the engaging session we've just had. At this stage, I'd like to call on Mr. Jim Oliver, who's the chair of Simon in Ireland. Maybe we both thanks.
Yeah. Okay, just call on me then to give a vote of thanks for this evening. I'd like to thank Engineers Ireland for co-hosting this event with ourselves and for sharing their facilities here in Clyde Road with our silo members. I'd like to thank all of you for attending. I think tonight's event has been very well attended. It's one of the best attended sessions I've seen in recent years. And finally, I'd like to thank the speakers, and maybe to summarise, that Peter gave us a general overview on integrated catchment management. Ray gave us our case studies on ICM and how they can help us carry out complicated modelling scenarios, and it's gone from 48 hours now down to 16 hours. I'm just mindful of my 9-year-old son at home yesterday who was getting frustrated with his FIFA 16 on the PlayStation when there was a time lag of a second. So maybe in a couple of years' time we might be able to get it down to a couple of hours or maybe in a couple of minutes. And then finally, Colin, for outlining quite clearly the implementation challenges, and that we've already covered in many respects the engineering solutions are a simple part, and actually getting the things built and funded are the complicated things. So without further ado, I'd like to propose a vote of thanks for all our speakers here tonight.
Thank you very much, and thank you very much to everybody here for attending this evening's joint session between ourselves and Simon and the Engineers Ireland Water and Environment Society. Just one or two housekeeping rule matters before we go. We have a visit of the ICE President, Sir John Armitt, in the 18th of February, and there's a breakfast presidential address that morning here at the institution at 9 AM. The other, I suppose, matter just to draw people's attention to is our next lecture That's the Civil Division, I must say. And that's on the 22nd of February here as well, and that's on Rosie Hackett Bridge. So you're all very welcome. That one's at 6:30 here, so you're all very welcome to that. Thank you very much.